welcome to lecture number 18 of VLSI Design KEC 072. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. Today, we are going to start our next topic in the series, which is related to pipelining design in sequential CMOS circuits. Okay. So, till now whatever we have discussed or analyzed, that involves some kind of a cascading in some form or the other. Okay. Whatever circuits we have discussed, whatever examples I have shown you or whatever analysis we have done, that involves some kind of a cascading operation. Okay. The output of the first stage reaches the input of successive stages either directly through an inverter, through a buffer or through some other circuitry, but in spirit it remains a cascaded version. Okay. That has a lot of advantages in terms of implementation, understanding it is quite simple, but as the size and the functionality requirements increases, from the performance point of view, every CMOS circuit is analyzed in two parameters. One is known as delay, another is known as power consumption. As the circuit density increases, as the complexity increases, the amount of delays increase when the number of devices increase, and when the number of devices increases, the heat dissipation goes up, and when the heat dissipation goes up, the static power consumption also goes up. Okay. For all these performance challenges, we have another way of rearranging or designing sequential circuits, which is known as pipelining. Okay. It is a popular design technique which is often used to accelerate the operation of data paths in digital processor. So, we can accelerate how input makes its way towards the output in a different form, in a different path, in such a way that the time it takes for its transition is reduced. So, pipelining is a technique to improve the resource utilization and increase the functional throughput, right. And this equation which is being shown on your screen here, that is the minimum clock period required for the circuit which is shown in the figure. Okay. So, first I will just explain what is this figure is. You have two inputs A and B. Okay. So, you have two inputs A and B. They are being stored in some registers which are clock triggered, edge triggered registers most likely. They are going through an adder circuit, then the absolute value is taken, okay, and then the logarithmic value of that absolute value is calculated, and that is stored in another register. So, this circuit, what it is doing at the output, it is calculating the log of A plus B, absolute value. Okay. Obviously, you can't get the log of a negative value. Okay. So, you need the absolute value. This circuit is calculating the logarithm of the addition or the absolute value of two added numbers. Okay. It has three stages. It has an addition stage, it has another stage which takes the absolute value, and it has another stage which calculates the log. Okay. So, it has three combinational logic stages. The minimum clock period required for reliable operation, okay, takes the propagation delay for the signal to reach the output, plus the setup time, plus the worst case logic delay. Okay. So, all these delays put together, all these timing constraints put together, add them, the minimum clock period required should at least be equal to these delays, so that the delay of each stage is taken into account. Now, this is the conventional implementation. We have another way of implementing. Okay. What if we introduce registers between the logic blocks? Now, what was the problem in the previous stage? If you see here, when the clock triggers here and A reaches at the initial combinational block of adder, okay, there are three different stages which are working in such a way that one is active only for 1/3 of clock period, because there are three stages. So, each stage is only active for 1/3 clock period. For the remaining 2/3 clock duration, clock time period, okay, for the remaining 2/3 period, there is absolutely no use of two of those logic stages. Okay. So, that is not a very intelligent use of resources, where your one of the logic block is only active for 1/3 of clock period. Okay. And if at one clock period it takes adder, at the next clock cycle it will take absolute value, at the next clock cycle it takes the log. So, to get the first output of log of a plus b, you need to wait for 3 clock cycles, and for subsequent outputs you need to wait for 3 more clock cycles every time. So, if this is a stream of data at a and b, you will have for n data sets, you will have to wait for 3 times n number of clock cycles. Okay. So, that takes a lot of time. What if we introduce registers between each block? So, what will happen is that first addition will be calculated here, that will be stored here. When this triggers, absolute value will be calculated here. When this triggers, log will be calculated here. So, initially you take 3 clock cycles to get of a plus b of the first data set, but by the time you reach here, you would have already calculated addition of 2 more data sets, and you would have calculated the absolute value of another data set. Okay. So, in this case what is happening is that when the result for first data set appears at the output after 3 clock periods, by this time this register is holding the absolute value of A2 plus B2, and this is holding, this register is holding the added result of A3 and B3. Okay. So, in the next clock cycle you will immediately, in the 4th clock cycle you will get log of A2 plus B2, in the 5th clock cycle you will get log of A3 plus B3. So, instead of waiting for 3 clock cycles every time, after the first result you are only waiting for 1 clock cycle for each result. This is known as pipelining implementation, or a pipelined implementation to obtain sequential circuits in CMOS. Okay. What it is only doing, it is only a small rearrangement. Okay. You are adding some extra registers, which does add some extra circuitry, but it provides a lot of other advantages. It reduces the amount of time it takes for the input to reach the output in subsequent clock cycles. Okay. The major advantage can be understood in terms of how much is the minimum clock period required. For the conventional approach, okay, the first circuit which I had shown you, the minimum clock period required was the addition of propagation delay plus the setup time plus the worst case delay paths. By worst case we mean that the maximum amount of time basically it is going to take. First it is going to pass through an adder, then it is going to pass through an absolute value calculator, and then it is going to pass itself through a log. Okay. So, all the delays of each stage add up, right, and that produces a constraint on the minimum clock period required. For the pipelined version, you do need the propagation delay, plus you only take the worst case propagation delay of that logic block, okay, which has the maximum delay associated with it. So, if you have 3 stages in this case, you have one adder, one absolute value calculator, one logarithm calculator. Among these 3 combinational logic blocks, the block which has the maximum delay, you only take the value of that block, okay, because if you take that into account, the maximum value into account, by the time that much delay occurs, the other 2 would have already calculated their outputs. Okay. So, you only take the worst case scenario, only take the maximum. This is sort of a parallel version of a series operation. Okay. And there is no setup time basically, because the input is always present at your first stage, and by the time it makes its way to the output, you are subsequently calculating different stages. Okay. So, setup time is not included here. So, what you can see here in this equation, that the minimum constraint, the constraint of a minimum time period of the clock is considerably reduced for a pipelined version. Okay. for n number of logic stages, if I have here I have shown you an example of 3 logic stages. Okay. If you have n number of logic stages with equal propagation delay. Okay. So, we assume that all the n number of stages have equal propagation delay. The pipelined version reduces the clock period requirement by a factor of n, where n as you can see is the number of logic stages. This increased performance, it comes at a cost of some additional registers. Okay. Here we have introduced 2 extra registers, one after each stage. Okay. But that is a very small cost. Okay. It increases latency. So, the amount of delay which happens before the output is actually calculated, that is considerably reduced. Okay. So, pipelining, as you can see with these advantages, because it offers an advantage on a very major performance indicator, which is the delay of a circuit. So, it is quite a popular implementation technique when it comes to high density circuits, okay, where there are a lot of data paths between input and output. Pipelining is a very useful approach. Okay. So, let us discuss now. This is the introduction and the advantage of using pipelining. Let us just see how you can actually implement a pipelined circuit. Okay. So, this is one way of doing it. This is known as a latch based pipelined circuit. Now, we are not using edge triggering, we are using latches for better flexibility basically. Okay. So, the pipeline system can be implemented using pass transistor based positive and negative logics. Okay. So, here when clock goes 1, input gets sampled on node capacitance C1, its inverted form in bar goes to F, and F is a logic block, combinational logic block which calculates. So, the output is taken here. Okay. At this time clock bar is 0. So, this is off. When clock bar goes to 1, whatever output was here is going to C2, its inverted form comes here and logic block G is calculated, right. And then in the subsequent clock cycle, when clock goes 1, whatever was calculated first by block F, then by block G, it comes here and then your output is obtained. Okay. Now, the requirement is that the clock should be non overlapping. Whenever there is overlap between the clocks, it is possible that the race between previous and present inputs will occur. Okay. So, the condition for this latch based pipelined circuit is that the clocks should be non overlapping, right. Again, this is just showing you what I have just explained you now. When clock is 1, block F gets computed, result of F is stored on C2, and when clock bar goes to 1, logic block G is computed. Okay. If clocks overlap, then there is a race condition between previous and current input. So, this is a latch based approach of obtaining pipelining, right. If you want to make an improvement on this race condition, in our last lecture we had introduced this concept of C2 MOS structure or clocked CMOS structure. You can use that approach for implementing pipelined structures in sequential CMOS. Okay. So, what was clocked CMOS register? You use a PMOS here and NMOS here, a PMOS here and NMOS here. They are being driven by opposite polarity of clocks. Okay. So, you see here, if clock bar is 0, which means when clock is 1, clock bar is 0. Okay. Suppose clock bar is 0 and clock is 1. So, the inverted input is sampled here. Okay. So, in bar gets sampled here, logic, there is some combinational logic here which gets calculated, the output reaches here. Okay. Now, in the opposite cycle, when clock goes 0 and clock bar goes 1, the inversion of this signal here appears here. Okay. So, F bar is going to appear here. Then this combinational block G will do its work, whatever combinational logic you have here, that appears here. Okay. And then finally, the output is going to be obtained here. This circuit will avoid the problem of race as long as the logic scheme or the logic mechanism of combinational block F is non inverting. Okay. So, in that case you are going to avoid the problem of race which happened in a latch based pipeline circuit. Okay. So, what we are doing? We are trying to implement some series some kind of a connection, some kind of a circuit arrangement where this advantage of pipelining in sequential circuits can be exploited. Okay. We have seen the advantages of pipeline circuit, now we are seeing the implementation. One way of implementation is a latch based circuit, another is a C2 MOS based pipeline circuit, which basically tries to avoid the race problem in a latch based circuit. Okay. Going forward, there is another version which is considered to be quite better as compared to your latch based pipeline circuit or your C2 MOS based pipeline circuit. Okay. The idea or the objective is still to avoid racing condition between inputs and outputs. Okay. So, we use what is known as NORA CMOS. NORA stands for no race. Okay. And a NORA logic block, first we understand what is NORA logic block. Okay. In some of our previous lectures, when we introduced the concept of dynamic CMOS circuits, we studied a topic known as domino CMOS logic. In that domino logic circuit, we were facing the problem of race condition. Okay. And to solve that, we introduced what was known as NP CMOS logic. Okay. NP CMOS logic was a cascaded version of N and P blocks. The NORA logic block is quite similar to that. Okay. In fact, the NORA logic and NP CMOS logic are sometimes used interchangeably, okay, because the way they are connected is quite similar. So, a typical NORA logic block will have an NMOS logic circuit, which is also known as a pull down circuit. The output of this pull down circuit acts as input to another PMOS logic circuit. Okay. Here it is known as a pull up network. Okay. Here it is known as a pull up network, right. The output from here acts as input to another NMOS logic circuit. The output here can go to another NMOS stage, the output from here can go to another PMOS stage. Okay. So, you have alternating arrangements of N block, P block, N block, P block connected in alternating fashion in such a way that the output of a preceding stage acts as input to the successive stage. Okay. There are certain transistor connected to clock. So, there is a PMOS connected to clock here, shared by an NMOS here. Clock bar is shared by a PMOS here and an NMOS here. Okay. So, this is a typical NORA logic block, right. This is still a standard dynamic sequential circuit only. Okay. Just to understand how it works, let us just say that phi here is equal to 0, the clock here is 0. In that case, this output, if I call it node 1, this pre-charge itself to VDD. So, the first stage here is in pre-charge stage. Okay. This is one here. So, this PMOS is off, but this is one here. So, this is on. This is discharging here. If I call this as node 2, this node is discharging here. Here phi is 0. Okay. So, the output here is again pre-charging. So, when clock is 0, the NMOS stage is pre-charging, another NMOS stage is pre-charging, this stage is discharging. Okay. So, NMOS stage is pre-charging and PMOS stage is pre-discharging. Okay. So, the output, the load of first stage goes high, the load of second stage goes low, okay, and so on, right. Now, when clock goes high, this is off, this is on, and some evaluation is happening depending upon what is there in NMOS logic. When this is 0, this turns on, okay, and this is 0. So, this turns off. So, this node 2 might go to VDD depending upon this logic, or it might hold its previous value. Okay. The idea is whenever clock goes high, the NMOS logic evaluates itself, okay, and when clock goes low, the PMOS stage pre-discharge itself and gets ready for the hold stage. Okay. This is a typical NORA logic or no race logic block. Now, how do we use it for a pipeline structure? Okay. Our main topic of interest today is to implement pipelining design technique, so that we can reduce the delay of our circuits, of our sequential CMOS circuits. Okay. So, we use what is NORA CMOS for pipelining. Okay. It combines two things, it combines the clocked CMOS version and it combines the NORA logic block, which we have just discussed. Okay. So, you have two things, one your clocked CMOS register, right, which avoids the problem of race, and you use the NORA dynamic logic block, okay, which is an alternating connection of an N block, P block, N block and P block. You combine these two in such a way that it allows you to implement pipelining without any race condition. Okay. So, the C2 MOS part of this circuit or the clocked CMOS part of this circuit is considered as the latch part, okay, and the NORA dynamic logic part is known as the logic part of this circuit. So, you have two elements, one logic, one latch, logic for calculation, latch for storage. Okay. These two are connected in such a way that that you are going to have a particular set of a module. Each module is going to have this NORA logic block followed by a clocked CMOS register for or latch for storage. Okay. And they are clocked in such a way that you always have two modules. So, each module has logic and latch, right, and there are two modules, one is called a clock module or CLK module. Okay. Whichever block is doing evaluation when clock is 1 is known as a clock module, while the other module is known as a clock bar module. Okay. So, you have two things, number one, a clocked CMOS latch circuit for storage and a NORA logic block for logic calculation. That particular block or module which evaluates when clock is 1 is known as a clock module, okay, and the other module is known as a clock bar module. So, see how the circuit looks like. The circuit on top is your clock module, CLK module. This here is your NORA logic block, okay, and this here is your C2 MOS latch. Okay. So, you have a say pull down network consisting of NMOS, all the inputs applied here, supplying its output to a pull up network, right. So, when clock goes 1, your NMOS is evaluating, okay, and when clock is 0, it is charging, this sub part is charging, this is discharging, and when clock is 1, this is evaluating, okay, and your output is taking the value depending upon whatever logic is there. So, and whatever output comes here when clock bar goes 1, okay, which means when clock goes to 0, okay, or you can say when clock goes to 1 here and when clock bar goes to 0, sorry. In that case, whatever output is taken from the logic block is being latched at the output in the inverted form. Okay. So, when clock is 0, your logic stage in the CLK block, this is your CLK block, when clock is 0, your logic block is pre-charging and your latch stage is hold mode. Okay. Same CLK block, when clock is 0, your logic is either evaluating and latch is also evaluating, right. And when clock is 1, your CLK block starts to evaluate, okay, and your latch also starts to evaluate for storage. The opposite is shown here, this is your CLK bar module, right. This has your pull down network sent to another logic block, okay, and then this is your latch circuit. Okay. So, combinational logic and latch circuit. That particular module which is evaluating when clock bar is 1 or when clock is equal to 0, that is known as a CLK bar block. Okay. So, this particular implementation is known as a NORA CMOS implementation for pipeline structures. Okay. You can use the NORA CMOS logic independently also. In that case, it will be considered as a conventional dynamic CMOS circuit, or you can connect your NORA logic block in series with a clocked CMOS register to produce a pipelined approach. Okay. So, with this we come towards the end of this lecture today. Let me just summarize what is NORA CMOS for pipelining. It basically consists of a data path between input and output in a chain of alternating modules of clock and clock bar. While one class of module is pre-charging with its output latch in hold mode, It preserves the previous output value, and while the other class is evaluating, data is passed in a pipelined fashion from module to module. Okay. It is highly flexible. Okay. So, in the combinational block, in the logic block, you can include both dynamic and static logic. So, it allows mixed logic design also, and complementary clock modules can either be cascaded or pipelined. So, if you only use the basically the logic module only, you are working on a cascaded version, or otherwise you are working on a pipeline version. So, it allows you both. Okay. So, with this we end today's lecture. We have done an important topic and quite interesting topic, which is based on pipelining design approach in CMOS circuits, where you use a different type of an arrangement, so that better utilization of resources can be implemented, the way input signal travels towards the output and it minimizes delay. There is a latch based version of pipeline structure, there is a C2MOS clocked CMOS version, and most importantly a better version is known as a NORA clocked CMOS version, which allows you a no race alternative to a pipelined design. Okay. So, with that we end today's lecture. Thank you.